Welcome back my dear friends, a very good morning, good afternoon, good evening to all those participants and students who are taking this TQM 2 under the NPTEL MOOC. And today is the 10th lecture, which is basically the last class for the second week, and after that you will obviously have the second assignment coming to you. And as you know, I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, yesterday when we started of the design of experiments, obviously we did discuss that ANOVA, so which is analysis of variance. So, you want to basically understand what is the total concept of variance. So, variance can be of two components. One is the sum of squares, which is the total error which you have, that is basically divided into two components, which is, now listen to me carefully, one is the error which is intra and one is the error which is inter. So, that means if you see for example a number of classes considering the treatments which we considered, and each class has n number of observations. So, we will pay more attention to the errors which is there in each and every class and also amongst the class. Based on that we formulated the hypothesis. So, the hypothesis were, number one, whether the means were equal, and we modified that to trying to find out whether the taus was 0. So, that is the null hypothesis which I am stating. With respect to the alternative hypothesis, that for the first case where the means are equal, I said one of them would be unequal, any two of them would be unequal, and in the other case for the tau, the alternative being the tau being not equal to 0. And we saw that when you are trying to compare the means, obviously I did mention we will always consider the z or the t distribution, and with the corresponding degrees of freedom being calculated based on the fact that what is the loss, which loss of information. Degrees of freedom reducing means you are losing, loss of information is there because you are not able to utilize the sample to that extent which would have been possible if there was no loss. And later on we saw that when you want to compare the standard deviation, the variance with respect to the errors, so we consider them to be all equal, and in another case the variance is not equal, at least two of them are not equal. And we saw that when we are comparing the ratios of the variances of the population, we took the F distribution, but the F distribution has the corresponding degrees of freedom calculated accordingly. So, it can be either less than type, greater than type, or not equal to, depending on whether you are trying to take the left hand side of the F distribution, right hand side of the F distribution, and the middle portion. So, we did discuss this, and we discussed that a very small example and how it could be found out. And obviously, if you remember, till the almost the fag end of the 7th class, we did we were in depth considering the concepts of hypothesis testing, before that point estimation and interval estimation. So, those concepts would be just for a precursor and they would be utilized time and again. So, with this small background or recap, let us start the 10th lecture. So, we now present the estimators for the parameters in the single factor model. Now, in the single factor model you have the yij, I being for the suffix corresponding to the nomenclature, that is the treatment, j is the number of observation which you have. So, that will be equal to average of the average mean, which is mu without any suffix, plus tau I, which is the plus and minus variations or the movement on the positive or the negative direction would you have for the mean for any any one treatment. I am talking the example, the etching example. And epsilon ij would be the errors, and if you remember I did mention, and it is very important to note that the errors are independent of each other, that is why the errors variances are all sigma square, and as assumed the expected value of the errors are 0. So, if I find out the mu hat is basically the estimated value of the mean, that will be y bar dot dot, because you are summing up for both the samples for any treatment as well as for all the treatments, and the mu hat, the tau hat is basically for the ith treatment would basically be that you will sum up for any treatment, sum up all the y values, find out the averages and find out the difference of this average with the averages of the averages, which is basically y bar dot dot, or which is also mu hat. Hat is basically the estimated value which you want to find out. So, here as I mentioned, I values will always change from 1 to a, and the j value would always change from 1 to n. A confidence interval can be found. So, the confidence interval estimate of the ith treatment mean may be easily determined. The mean of the ith treatment, as we know, would be equal to mu I plus is equal to mu plus tau I. So, obviously, the error terms would not come. So, this tau I would basically give you the so called movement in the positive direction or the negative direction of the sample mean corresponding to the fact that what is the average of the averages, which we find out by y hat dot dot. Okay, sorry. So, a point estimator of I would be basically be the hat value mu I hat. So, that will obviously will be equal to the sample average. So, that is what that would be basically mu I hat plus tau I hat. So, tau hat, as I mentioned, again I am mentioning it can be positive and negative. So, that will be given by the averages of each sample. So, if it is basically the first row, so you will add up all the values and find out the average. That is the best estimate for mu I hat. If I go to, say for example, the 8th treatment, if I add up all the n observations which I have for the etching, divide by the number of observation which is n, that average which I find out would basically be the best estimate for mu hat suffix a. So, you can find it out accordingly. Now, if I want to find out the confidence interval, so now I will pause and explain. Now, if you remember, we did discuss, and I would repeat it time and again, that when you hear what is the aim. So, let us pause and think. The aim is to basically to find out the mean value. So, if it is mean value, immediately the bell will ring in your mind that you can use any of one of the two distribution, which is the Z1 and the T distribution. Now, you will ask yourself why Z is not being used, because in the Z distribution we know the population variance sigma, here we do not know. So, if we do not know, we will utilize the value of T distribution. Now, when it is the T distribution, you will ask that if I need the population variance, and if we do not have that, what is the best estimate? It is the standard error square of the sample. So, it is the standard error of the sample. So, there can be two formulas, one is with the S and one is without the S dash. So, if it is obviously without the S dash, you will use and for both the S without the dash also. So, you will basically use the T distribution. Now, the T distribution would have a degrees of freedom, that degrees of freedom would be decided by the fact whether you is using the S dash or S without the dash. So, coming back to here, we will be using and based on that we will proceed. So, you will be using the T distribution as rightly thought by all of you. So, if the confidence interval we want to find out, so obviously there would be the x bar n which you had. So, I have to try to write it down. So, what you had in this equation, in the simple case you had x bar, and I am writing both the plus and minus to denote the left interval and the right interval. So, plus would be for the right, minus would be for the left. Here t, this was n minus 1, and correspondingly it was one sided, obviously it will be alpha, or it can be also denoted by 1 minus alpha depending on what is the actual nomenclature you are doing, and obviously you will have S n and the value of n would be coming. Now, pause here and look. So, let me change the color and I use the highlighter one. So, if you use this, this is akin to the case that you are using the sample mean. So, the first part one to one correspondence makes sense. Then I use the concept of Sn. So, obviously that would, so that is the square root. So, that will be the mean square which is here. If I use, again let me change the color, if I use square root of n, this is the square root of n which I have. Then if I use the case of, let me use another color, the brownish one. No, that will that is red in color, so it will be difficult for me to find out. Okay. So, if I use Tn here and here it is also T, I am sorry it is too dark, excuse me. So, here Tn n minus a is the degrees of freedom which we have already calculated. Here it is the degrees of freedom is 1 because you are losing 1 degrees of freedom corresponding to finding out the sample mean as the best estimate for the population mean. Now this will make sense why it is capital N minus a. So, how many such samples are there? There are A samples because we are doing 8 number of treatments. So, for each of the treatment we need to replace their population mean with respect to the sample mean. So, you lose 8 degrees of freedom, hence the total degrees of freedom now as present would be capital N, which will be small n into a minus a. So, I will now remove the colors in order to give the corresponding values. So, this would be done. Oh, I lost so let me use it. Just give me 1 minute. So, I have been able to replace all the highlighted colors without deleting the equation, but only Tn vanished. So, let me write down the Tn1. This is Tn minus 1. Now, if I go to the color, so this Yn technically will correspond to something here. This MSC will correspond to here. This N would correspond to square root of n. So, this is square root also. So, I am just giving a 1-to-1 sibling, and this Tn with n minus a would correspond to this. So, now it will make sense that for only one population with respect to, say for example, separate a number of populations, how we can find it out. So, now here it will make sense. So, the plus and minus signs would be coming. Plus is for this case where you have the upper limit, low m, minus is the case when you have the lower limit, and this ms suffix e is the mean square error which you have. So, 100 into 1 minus alpha interval. So, 1 minus alpha would be the total area covered in between. Confidence level is the difference between any two treatments means. So, hence we can find out that if I want to find out the difference in the means. So, obviously the difference would be means. If you remember, when you are trying to find out the difference of, say for example, the average of the jam bottles being produced in factory 1 and factory 2, considering the this null hypothesis was the case when we considered the mean difference for the population for these two factories of products coming out is to be 0, and for the other case it is not 0. So, this is 0 and that is being replaced by x bar n1 minus y bar n2, where n1 and n2 are the sample sizes which I am picking up from population 1 and population 2. And again, so this would make sense for me. Again, this is x bar n1 minus y bar n2. So, n1 n2 are basically n with a suffix 1 and n with a suffix 2. So, that would make the concept clear to you. And this is again a t distribution. So, on the left hand side, technically it would be this value which I am just now highlighting slowly. This is 1 minus alpha by 2, because this is both sided. This is alpha by 2. The degrees of freedom in the initial case when you had 2 population, remember, pause here, it was n1 plus n2 minus 2, because you are losing 1 degree from population 1 or from the sample which you are taking, and this next one was from population 2, which was the sample 2. Now, if you consider that how many such samples you are taken, you have taken a of them, hence you lose the total degrees of freedom losing which is being lost is a, hence it is now capital N minus a. Using the data for the example 3.1, we may find the estimates of the overall means and the treatment effects as mu hat being equal to the total value divided by 20. 20 was because there were 5 readings in each etching or treatment, and there are 4 such powers, 160, 180, 200, 220. So 12,355 the total sum divided by 20 would give you a value of 617.75. So from that, if I find out the tau values, tau 1, tau 2, tau 3, tau 4 with the hat obviously, because the estimated value comes out to be minus 66 point, I won't repeat the decimal, it is minus 66, minus 30, plus 7 and plus 89. So a 95% confidence interval on the mean of the treatment for those 4 is computed, and we find out the means accordingly. So it is found out for the 220 what. So obviously the 220 value is 707. So this is the mean value, and this mean mu 4 was basically the average which I am trying to find out. So it is not the technically not trying to find out the so called differences. So this t value is given 2.120, 2.120 with a minus and a plus sign depending on which side it is on the negative side or the positive side. And remember the value of degrees of freedom would be capital N is 20 minus a is 4, basically 20 minus 4 it will be 16. And the alpha values as already given depending on the on this. So this is basically 95% confidence level. So alpha would basically be 1 minus 0.95. So that is both sided. So you will divide by 2 and find out the values. So of t. So you put them. So this is the mean square which is coming out to be the value of 33.70 divided by 5, because 5 is the sample size for each group which you have, means each treatment etching. So based on that you find out. So thus the desired 95 confidence levels values are 689. I am again not mentioning the decimal, and the upper value is 724. So you similarly you can find it for 200, similarly you can find it for 180, similarly you can find it the value of 160. Now in the case when you want to find out the values of the interval for the case when it is 160, so in case of 707 you will have this 551.20. So this gets replaced by 551.20, this gets replaced by 551.20. The value of 2.120 and plus and minus remains the same, because the sample size for each and every treatment n is constant here. If you remember that I had mentioned that when we were doing the problem, and hence the t values remain the same. This n value which is 5 is basically the same, and we do the calculations accordingly, and obviously alpha value is same here. So if you want to change the values of alpha, you will get what the changes you would have for this problem, which is just shown on the slides. For the 220 watts would be the t values would be changing, because then the t values would basically increase or decrease depending on the confidence level value which is changing, because in that case alpha by 2 value would also change, because if it is 90% confidence level, so in place of 95 you will basically have 90, so it will be 0.1 minus 0.9 and divided by 2, that is alpha by 2. In some single factor experiments, the number of observations taken within each treatment may be different. We then say that the design is unbalanced. So now here is the main point coming. If you remember, I mentioned at least 3 or 4 times that the number of sample size n is fixed for each and every treatment. Now if they are changing, so if they are changing, so they are unbalanced. So the manual computation formula for sum of squares of the totals and sum of squares of the treatment become now. So in this case it will be, when you had summed up, if you remember, I now use a highlighter one, so in order to make things easier, and use so this value which you have n suffix I for each and every treatment was fixed, was small n only. Now it is changing. So when you sum up y square suffix ij, so these values of j would change from 1 to n1 for the first case, 1 to n2 for the second case. Case means the treatment, and correspondingly, and I value will change from 1 to a depending on the number of cases, which is cases of the treatment is a. So from, and obviously you will still use the formula of capital N being equal to that will be basically be n1 plus n2 plus n3 plus n4 till dot dot till n suffix a. So, the S of the treatments, suffix of the treatments would basically again the square of the difference, that is y square I dot, dot being for the sum of all the corresponding values of each and every row separately. So, I is basically along the column. So, I am just repeating it to make it much more clear and sensible to all of us. So, you will find out the differences minus y square double dot, that means the values summed up for all the values along the rows, along the columns, divided by capital N. Now, the capital N value which you know. So, capital N, I am using the highlighter, but the formula should definitely would not change, it remains the same. So, it will be for the first etching till the last etching. So, in the initial case each one of them were N. So, no other changes are required in the analysis of variance. There are two advantages in choosing a balanced design. First, the test statistics is relatively insensitive to small departure from the assumptions of equal variance for a treatment if the sample sizes with respect to the treatment where the sample sizes are equal. This is not the case for unequal sample sizes, because and obviously the sensitivity would be very high. And second, the power of the test is maximized if the samples are of equal size. That means the overall efficiency which you want to find out is the maximum. Model adequacy checking. The single factor model works on these following assumptions. Number one, the errors are normally distributed and independent. So, independent means they are the overall variances of all the errors are fixed, which is sigma square. They are normally distributed. So, it is normal with mean 0 and variance is sigma square. So, which is mentioned here with mean 0 and constant, but unknown variance is sigma square. If these assumptions are valid, the analysis of variance procedure is an exact test of hypothesis of no difference of treatment of the means. In practice, however, the assumptions will usually not hold exactly true, because the errors are basically dependent. Consequently, it is usually unwise to rely on the analysis of variance until the validity of these assumptions can be checked, and we can use the formulas accordingly. The violations of the basic assumptions and model adequacy can be easily investigated by the examination of the residuals. Residuals are the errors. So, if I find out the errors are basically for each and every values, it will be yij for any particular value. So, in the case of the treatment with respect to the number of samples in each treatment being 5 and number of treatment being 4. So, obviously, it is basically a 4 by 5 matrix, 4 being the number of rows and 5 being the number of columns, rows corresponding to the treatment, columns corresponding to the sample sizes. So, each cell yij minus y hat ij, which is basically the average estimated values which we find out for those. If y hat ij is an estimate of the corresponding observation yij obtained, then obviously yij can be found out, and obviously the yij would be equal to mu hat minus tau I. So, which can be expanded further and find out that y hat ij is equal to y bar I dot, which is basically the average of all the values for any treatment along the row. If the model is adequate, the residual should be structureless, that is, they should contain no obvious patterns and they would be random, but with the errors, remember, they would basically have a mean value of 0 and variance of sigma square for each samples. If I increase the sample and repeat it time and again, the errors would come out to be averages 0 and the variances would all be equal to sigma square, which is in practical sense may not be true. So, the normality assumptions, a check of the normality assumptions could be made by plotting a histogram of the residuals. Residuals means the epsilons which I am calculating. One way is to construct a normal probability plot of the residuals. If the underlying error distribution is normal, the plot will resemble a straight line, because I am taking the QQ plot. So, it will be a 45 degrees line. So, here I am finding the residuals which I just highlighted. Here the normality plot for the percentage probability. So, this 45 degrees line would mean that I am covering this percentile of the residuals, and then the corresponding for the theoretical distribution which I have in front of me, against which I am trying to compare the residuals would also be obviously it is a normal. So, in that case the percentile coverages in both these cases are equal. So, technically the line would be a 45 degrees line, such that each point would correspond to any one point along that straight line. That's the theoretical construct. So, now obviously, in this diagram which you see, they are not on the 45 degrees line, but they hover in and around the 45 degrees line. So, giving us some confidence that the residuals are normal. So, obviously, just this I am a little bit digressing from the discussion. If there are more onto the upper part at the later portion, or the lower part in the initial portion, or they are more on the upper part for the initial portion or below the line, I mean the below portion. So, they would basically mean they are skewed either onto the left or to the right, depending on what type of distributions which you have taken. So, this is just for the information. People must have seen all these histogram plots, the QQ plots, which is the quantile quantity plots, which will give you a lot of information. Because the F test, the F distribution test is only slightly affected, we say that the analysis of variance and related procedures such as the multiple comparison is robust to the normality tests as assumptions. A very common defect that often shows up on normal probability plots is one residual that is very much larger than of the others. Such a residual is called such a residual is also called the outlier. That means outlier of the actual value, it's very high or very low. The presence of one or more outliers can seriously distort the analysis of variance. So, when a potential outlier is located, carefully investigation should be carried out. A rough check of the outliers may be made by examining the standard residuals. So, I have basically the errors divided by the square root of the mean square errors. So, that should basically give me what if there are outliers, and obviously we know the errors are normally distributed with 0 mean. I am repeating it, with sigma square as variance. The standardized distribution should be approximately normal with mean 0 and a unit variance in the standard case. Standard case means I have considering the variances as 1. Plotting the residuals in time order of data collection is helpful in detecting strong correlations between the residuals. A tendency to have runs of positive and negative residuals indicates positive correlation. This would imply that the independence assumptions on the errors have been violated. This is a potentially serious problem and one that is difficult to correct. So, it is important to prevent the problem if possible when the data are collected, and we can take corrective actions accordingly. Proper randomization of the experiment is an important step in obtaining the independent structure. So, it means if you remember that when we are doing the experiment of 160, 180, 200, 220, we randomly chose in order to do away with any error biases creeping up intentionally. So, let me use the word intentionally. That means, if we keep doing 160 and then go to 180, so that means there is slowly increase in the wattages, which may affect the etching and the other values which you are trying to calculate. Sometimes the skill of the experimenter or the subjects who are doing the experiment may change as the experiment progresses, or they may be biases creeping up. Being studied may drift or become more erratic. So, this would often result in a change in the error variance over time. So, this condition often leads to a plot of residuals versus time that exhibit more spread at one time as the time ends, or in the beginning or in the middle. So, which would give you some information that there is something wrong in the overall biasness which is creeping up due to some either unintentional, but we should definitely have taken care, or intentional based on how the experiment is going. So, with this I will end the 10th class and continue discussing about the ANOVA and the other ideas about design of experiments, and I would wish everybody have a nice day. Thank you very much.